Welcome to Block 6, the Mathematical Structures block. The structure we're going to investigate in this program is called the complex numbers. And we're going to get at it by trying to solve a quadratic equation. And we'll find that this will force us to extend our idea of what we mean by number. Well, let's see what the problem is. Consider this quadratic function. We've actually plotted it for a value of c equal to 9. Now, the question I want to ask is, what are the roots of the quadratic equation corresponding to that? That is, for what values of x is this function equal to 0? Well, from the picture, that's very easy. I can see it. It's just these two values. Now, suppose I change the value of the constant to, say, 40. Now, that just corresponds to translating the curve up. And now I can ask the question again, what are the roots corresponding to this new curve? Well, from the picture I can see there don't seem to be any, so we could just stop there and say, well, that's unfortunate. But mathematically, that's not very satisfactory. I'd like to be able to say a quadratic equation always has two roots. Now, where have the roots gone? Now, that's the question that's going to force us to extend our idea of what we mean by number. So let's take a look at the behavior of the roots of a quadratic equation. Initially, the quadratic has two roots. We can plot the roots on a copy of the real line r. See how the roots change as we alter the position of the curve. Here, they're coincident. A little below, two roots. A little above, no roots. And you could ask yourself, where are the roots going to? Well, where did they go to? Here are the roots corresponding to this curve, but where are the roots corresponding to that one? Well, there aren't any in this picture, so perhaps the picture isn't the right thing to use. Perhaps we'd be better if we tried an algebraic method, and that's what Jeremy is going to do now.
We have an algebraic method for solving quadratic equations, and that's the method we asked you to look at before the program. And if you remember, it uses the coefficients of the equation you want to solve and substitutes them into a certain formula. Now, I'm going to use that method to solve both of the cases that Alan looked at, this one here where there were roots and the other one where there didn't seem to be any. And if I do this and I take this formula, which is the one we use, and I substitute in the coefficients of the first equation, I get that, and that simplifies down to that, and I have the two roots. X is 5 plus or minus 4. 5 plus 4, which is 9. 5 minus 4, which is 1. And we find those on this diagram here. That's the root x equals 9. And this is root x equals 1. Well, that's very nice, but I can try the same method on the second equation with the coefficient 40 in it. When I remember to substitute that in, I get this, and that simplifies to this. And now we're in a mess, because this is trying to be the root of this equation, and yet, according to the picture, there are none. And at least we can see what the problem is. We can say that we don't understand what that root of minus 15 is. After all, a positive number times a positive number is always positive, and a negative number times a negative number is positive. So what kind of a number is it that when squared is negative? And yet it really is such an excellent candidate for the root of this equation. And that's what I want to look at now in a little more detail. It all depends on what we mean by the root of an equation. And I mean anything which, when I substitute it in place of x, in these brackets here, gives me 0. So let's take one of those numbers. I'll take 5 plus the square root of minus 15. I'll put it in both of the brackets, and I'll see what I get when I calculate with it. So I'll square up the first bracket first. 5 squared is 25, plus twice the product, that's 10 lots of the square root of minus 15, plus the second term squared. Well, the square of the square root of something must be the thing itself. So whatever that root of minus 15 is, its square anyway is minus 15. That's the first bracket. For the second bracket, well, minus 10 times 5 is minus 50, and then I have minus 10 lots of the square root of minus 15, and then I must remember to throw in my plus 40. So what have I got? I've got 4 terms I understand: 25, the minus 15, the minus 50, and the plus 40 at the end. And they add up to 0, so that's okay. And then the 2 terms I don't. Plus 10 lots of, whoops, the root of minus 15. Must be careful with these things. Minus 10 of the root minus 15. Well, 10 minus 10 of anything is 0, so these 2 add up to 0. The whole thing adds up to 0, and so 5 plus the root of minus 15, if only it behaves like a number, and we can treat it in this way, really is the root of this equation.
Well, algebraically that looks all right, but that's not really the question I asked. What I'd like to see is a picture with the roots of that quadratic on it.
Well, that's right, Alan, and I think we can get a picture out of this by remembering how we handled the number in the first place. We treated it in 2 parts, this working here, this working here. Suggests the picture should have 2 parts. And a standard picture with 2 parts in for a number is going to be a 2-dimensional coordinate plane, of course, and I've got one of those over here. Well, if I'm going to represent these new numbers on this coordinate plane, and I'm thinking of those new numbers as pairs, my question must be from the start, what is the pair that this number apparently supposed to be? I can take the 5 as the first member of the pair, but what about this mysterious square root of minus 15 that we don't really understand? I want, after all, a pair of numbers that I do understand. The 5 is all right, but can you see what number we should take as the other half of the pair? Well, it's a little easier if we rewrite it this way and take the square root of minus 15 as the square root of minus 1 times the square root of 15, because that number we really do understand. It's a real number, and it's a little bit less than 4. So I can take for 5 plus the square root of minus 15 as a pair, 5, and the square root of plus 15. And I'll put my number in this plane by going 5 units along for the 5, and plus, so I'll go up root 15 units to there. So that's where I'll put 5 plus the square root of minus 15. And what about 5 minus the square root of minus 15? What about this? Well, in the same way, 5 for the first member of the pair, root 15 for the second member of the pair, but I go down now because of this minus sign, 5 along and root 15 units down to there. So that's my picture. I can put the ordinary real numbers along here and the new mysterious parts of the numbers up here. And whilst I'm about it, I'll simplify my notation a little. I don't like this bulky root of minus 1. I'll write I instead, so I write expressions like this instead of expressions like that. And up this line I'll put, well, 5i, 10i and so on for these numbers, 15i. I've got a whole plane full of numbers, and in particular I've got a picture for the roots of that equation with which we began. They've gone off the line, all right, but they've gone into the plane here and here.
So the question, where did my roots go to, has been answered in such a way as to force us to extend our real line of numbers to a plane of numbers called C for the complex plane, because historically these number pairs are called complex numbers. Well, now I can confidently assert that our quadratic always has 2 roots. So let's take another look at the behavior of our roots. Using the real line, our roots only show when the quadratic cuts the axis. But if we extend our real line to a plane, the complex number plane, then we can see what happens to the roots. So our quadratic always has two roots, no matter where it's positioned. Well, perhaps this might extend to curves of a higher degree. For example, how many roots would you expect a cubic to have? Well, let's get our tame computer to answer that one. We can move the cubic and watch the roots as well. As well as moving the curve, we can change its shape and watch how the roots behave then. Let's look at a higher degree curve, a fourth degree curve. These are the roots. Well, we're getting the glimmer of a beautiful mathematical generalization here. We've seen every second degree equation's got two roots, every third degree has three roots, every fourth degree has four roots, and so on. This idea is so nice that we're going to devote the last television program of the block to it, where we'll also show in what sense complex numbers such as this give rise to zeros of curves such as that. Well, we've set out what we wanted to do. We've seen where our roots go to. They go to the complex plane. Now, the complex plane is not only beautifully useful for visualizing the roots, but we can actually also see operations on complex numbers, operations like addition and multiplication. Well, we know how to do addition algebraically, but what does it look like in pictures?
Addition of complex numbers is very simple. You remember when we calculated with them before, we kept the two parts of the complex number separate? Well, we just do that all the time. If I want to add 4 plus 8i to 15 minus 12i, I add the 4 and the 15 to get 19, and the 8 and the minus 12 to get minus 4. And just as I put 4 plus 8i there, and 15 minus 12i here, I put the answer 19 minus 4i here. That's one way to do the addition of complex numbers, thinking of them very much as coming in two parts. But instead of thinking of a complex number as a horizontal, together with a vertical, we could look at it in an altogether different way, as a line. Every complex number corresponds to a line from the origin. To add complex numbers, we just do this. It doesn't matter which order we add in, the result's the same. In each case, the answer is the diagonal. So, to add complex numbers pictorially, we think of them as defining a parallelogram, and we put the answer at the far end of the diagonal. Now, that's the addition of complex numbers. Can we find a picture for the multiplication of complex numbers? Well, we can. I've set up on this complex plane the multiplication of two complex numbers, 1 plus I times 1 plus root 3i. And it's very easy to find the answer algebraically. You just sit down and grind out the numbers, and the answer turns out to be this number here. Fine, but it's not very clear from this picture why we put the answer where we do. We want a pictorial way of thinking about this, and we're going to get the computer to do lots of multiplication sums for us to see if we can pick up a clue. We'll start with the same two complex numbers and their product. Let's see what happens if we change this one. We'll change it in a special way, so that its length doesn't change. While we rotate it, we'll get the computer to multiply it by this number, and to draw the product. As we change the numbers, the product changes too. Look at how it changes. The product always leads by the same amount. What is that amount? It's just this. To get the angle of the product, we add the angles. Let's look at that again. To multiply these two complex numbers together, we just add the angles. To multiply the one at the top by the one at the bottom, I add the angle at the bottom to the one at the top. Just do that, and we get the angle of the answer. But what about the lengths? Well, to get the lengths, it's easy to see. You can check after the program. This length is just this length times this length. And so we have a very nice picture for multiplication. We have a good picture for addition. And these are the operations that are basic to anything that wants to be a number. So we can use these pictures to help us out any time we have a problem involving either the arithmetic or the algebra of complex numbers.
To summarize, our mathematical structure, complex numbers, provides us with pretty pictures for addition and multiplication. It also gives us undreamt of solutions to all sorts of equations, and there are lots of other goodies besides. But let's just concentrate on one. This, corresponding to this fourth degree curve, which you've seen before, we have this fourth degree equation. And these are the four roots. So each of these numbers obeys that when I raise it to the fourth power, I get 1. Well, you probably have guessed +1 and -1 did that, but here are two complex numbers whose fourth power also gives me 1. Interesting. Let's concentrate on powers of a complex number.
Well, we know how to multiply complex numbers, so finding their powers is fairly easy. And I've started off here with b, and I found b squared and b cubed by adding the angles each time and multiplying the lengths. This is the start of a pattern, obviously. Now, how does it go on? Each time, the angle is the same, and the length is multiplied by the same amount. These angles are all the same, and the distances grow by the same factor each time. So from this beginning, we get that spiral. But complex numbers aren't the only things to spiral like that, as I'm going to show you. I have here the shell of a sea creature called the nautilus. We've had it cut open down the middle, and it's a very beautiful object. Each chamber is an enlargement of the one before it. But the really remarkable thing is that this spiral here, is exactly the spiral we've just seen, except that this one is the reflection of that one. These points are the powers that we've just seen. These angles are the same. In fact, the relation between the nautilus and the complex numbers is that they both grow along this curve. It's clear that I chose b for my complex number to have a length so that its spiral exactly matched the spiral of the nautilus. What would have happened if I'd chosen a different length for b? Here's the spiral we've already got. The basic complex number has a length greater than 1, so the spiral grows outward. Let's shrink our number. All the powers change too. When the basic number is shorter than 1, the spiral grows inwards. what happens when the length is exactly 1?
So this interesting sea animal grows itself in precisely the same way as a complex number multiplies itself. And of course, if we choose the right length of complex number, then we'll get a special case of the spiral, a circle. Now, what do we learn from that? Well, if this is the complex number b, by successive multiplication by itself, I get b squared, b cubed, and so on, stepping round the circle until b to the 15 is equal to 1. So b is a complex number, which when I raise it to the 15th power, I get 1. It satisfies the equation x to the 15 minus 1 equals 0. But from what we've already said, you'd guess there must be 14 others. Where are they? Well, let's look at b squared. B squared multiplied by itself gives me b fourth, 6th, and so on, stepping around the circle again until I take its 8th power, b 16th, and I just miss 1. But don't worry, when I continue the process, I step round the circle again, and of course, I end up at 1, but this time, the second time round. So that's another 15th root of 1. And of course, you won't be surprised to learn that on this diagram, we in fact have all 15. Well, that's incredible. Starting off with trying to solve a quadratic equation, we've actually been led to a geometric construction of the 15 15th roots of unity. Well, that's part of the charm of complex numbers. They look very simple, they are very simple, but they have a tremendous power. Now, in this week's work, we'll actually look a little bit further at the nth roots of unity. We'll ask interesting questions like, what do we mean by saying a complex number is prime? I think you'll enjoy it.